Today we're going to merge k-sorted lists. This is a very common interview problem. Given an input containing k different lists of integers, each individually sorted, output a list containing all the integers in sorted order. This problem is a good example of one that's easy to solve efficiently, but harder to solve optimally. This is a simple example of the problem. We have two sorted lists of integers, each containing 4 integers. When we combine them, we get one larger list of all the integers in sorted order. A first solution to this problem is very easy to come to. Start by initializing some output list. Then, for each of the elements in the input lists, add them to the output list. Finally, sort the output list and return the output. The runtime of this is n log n, which comes from the time complexity of the sorting operation. N in this case is the number of elements in all of the input lists combined. After we implement this algorithm, we'll look into a more optimal solution. The C++ implementation of the solution is slightly more complicated than the pseudocode, and this is mostly because we're using linked lists. The first thing we need to do is, of course, define our linked list data structure. Once we have this, though, you might be surprised to see that we initialize our output as a vector instead of as a linked list. This is simply because C++ has a native sort function for vectors already. If we want to implement our own sort for linked lists, we could use that instead. Then, like we planned, we iterate through all of the elements of the input lists and append them to our return value, in this case, the vector. Sorting the vector is also simple enough using the native standard library function. In order to convert the output vector into a linked list, we keep 2 pointers. The first is the pointer to the first linked list node. The second is a double pointer called current that tells us where to create the next node in the linked list at any given time. Every time we create a new node in the linked list, we update the current to the new next node. Finally, we return the starting node in the linked list that we saved. In order to come up with a more optimal solution, let's start with an example that has 2 lists. We're actually going to take a look at what the merge algorithm for merge sort does on this input. We start by looking at the first element in each of the lists. In this case, the numbers -6 and -2. Then we're going to take the smaller of the two and plop it into our return list. In this case, the -6. We quickly replace the -6 with the next element of the list it came from. In this case, the -1. Then, all we do is repeat this process. The -2 is appended to the output next and is replaced by the 0. Then, the -1 is appended to the output and is replaced by the 4. We continue to repeat this until we exhaust both of the input lists. Whenever one of the lists is emptied, we continue to append the remaining elements from the other list. This encompasses the merge operation for merge sort, where we need to merge exactly 2 lists. And this algorithm runs an O of n, where n is again the number of elements in both of the lists combined. This merge algorithm extends very nicely to larger numbers of input lists. Here we have an example with 4 lists. To start, we will look at the first element from each list. Then we will take the minimum of those 4 elements and append it to our output list. After replacing the appended element, we repeat this process. In order to efficiently choose a next element, we will keep all of the currently considered elements in a data structure that lets us easily find and remove the minimum element. This data structure is visualized by the large blue box to the left of our inputs. There happens to be a data structure for exactly this operation, a priority queue. Once one of the lists is completely emptied, we will still continue with the other lists, and we will simply repeat this process until we have exhausted all of the input lists and emptied the priority queue entirely. Once we're done, we will have a complete solution to our input. The pseudocode for this algorithm is quite straightforward. Create a list for the output result and a priority queue. Add all the first elements of each of the input lists to the priority queue. And then, until the priority queue is empty, remove the smallest element from it and add in the replacement from the same list if there is one. The total runtime of this algorithm is n multiplied by the time it takes to push and pop from the priority queue. Since we do each of these operations once for every element in each of the input lists. Typically, priority queues take logarithmic time in their size to perform each of these operations. This would normally give us a bound of log n, but their size is actually a little smaller in this case. They never have more than k elements in them at any given time. So overall, this gives us a time complexity of n log k, which is a slight improvement. The C++ implementation follows this almost exactly. We can use the same starting point as before with the linked list data structure and the function signature. Since we don't need to sort, we can directly initialize our return value as a linked list. We will also keep the same double pointer for the next element in the return list used in the last implementation, this time named current ret. The next thing we need to do is define the comparator for our priority queue. This is where we get a bit of extra complexity in the implementation compared to the pseudocode. In order to find our replacement values, we actually need to store the linked list nodes themselves in our priority queue. Thus, we need a custom comparator. The comparator itself can be defined as a simple lambda function. To use it though, we need to define the full set of template arguments for our priority queue. Of particular note is the last template argument, which needs to be the type of the comparator. We can get this using the decal type operator in C++. Afterwards, we add all the first nodes of the input lists to our priority queue, and then perform the main loop until it's empty. Finally, inside the main loop, we take out the top element in the priority queue, append its value to the return list, and then add the next list node to the priority queue, if there is one. Don't forget to update current ret, the double pointer. There are a couple of simple mistakes that can be made while implementing this. Don't forget to initialize the return pointer to a null or empty list. Also, make sure to guard against empty lists being pushed to the priority queue in the initialization. And lastly, remember to also pass the custom comparator to the priority queue as a constructor argument, in addition to the template parameter. And that's it. The full implementation of our optimal algorithm is complete, and we're done.